A very warm welcome to ATDI. Today we have a special topic to discuss in a webinar. The topic is based on current integration project for Search and Rescue Department in South Korea. The project was delivered with the help of a local partner. During the webinar, we will discuss how to prioritize search area by using state-of-the-art propagation tool HTZ communication by ATDI. The speaker for today is myself. My name is Yaya. I'm a senior spectrum engineer based in Sydney office. I've been with the company for nearly 10 years. So I will walk you through the webinar today. So I left my email and also full name in case you need to contact me. The topics to be discussed today, I've got these different topics I'm going to cover, but not necessarily in that order. So first we're going to lay down the mission scenario. What is the scenario we're trying to model? Also, I'm going to describe the architecture. What are the components, the planning tool, the database integration. Also, we're going to touch on the automation. In fact, I'm going to run probably a demonstration how automation is going to work. And also we're going to do coverage calculations and analysis. And we're going to touch also on the accuracy of the modeling. So first, the purpose, which is the mission scenario here. The purpose is to use the knowledge of RF coverage to further reduce the search area. So that's the idea here. The idea is we're going to use simulation tools, digital terrain model, CLADA, base station parameters, and so on to estimate the coverage more accurately, and also with the end goal is to reduce the search area so to minimize the risk. So let's look at the scenario here. So the scenario I have before me is there's a person lost, okay? It's a missing person. And all you know is the last concurrent seen towers or cells. So the carriers, for example, advise what is the cell ID or the cell ID or the cells ID of the last connected base stations. So this information is going to come very handy, of course, to do the analysis and then establish the search area. So here what we're going to do, we're going to deterministically find the optimum search area and fine-tune it even further. We're going to rely on the carrier or the regulator information. So we're going to get from the carrier the list of connected base stations or cells, and from the regulator we're going to get the public telephony system sites, the site locations, the technical parameters, and the transmission power, for example, antenna gain, and so on. So these parameters, if they don't exist, we could rely on some templates and existing assumptions. So we're going to use the knowledge of both connected and non-connected, and this is very important. So we're not just going to use the connected cells. Also, we're going to leverage the non-connected cells in order to further perfect the search area. So we're going to apply state-of-the-art radio propagations to fine-tune the search area. So here on the right-hand side, you see we've got two towers here, 4G, they are connected. So we know these two cells are connected to the missing person, but these 1, 2, 3, 4 are not connected. So we're going to use both connected and disconnected or not connected in order to try to reduce the search area. So first, let's touch on the concept. What is the concept behind this area reduction? So first let's go with the simple case where you know there's only one case where there's only one BTS connected to a target. So it's a simple case. So there's one tower, and the target or the victim or the person you're trying to locate is connected to that tower. So it could be anywhere in that area here. It could be anywhere. Okay, so this is a simple case where you only have one BTS. So your search area is limited to the blue circle. So I want you here to pay attention to this convention here. If you see a red antenna here, you see this one red, that means this site is disconnected. And if you see green, that means this site is connected. So this one here is connected. Now, if you have more sites are connected concurrently, so obviously this is limiting your search area. So you look at the overlap. So these two sites are connected, and then you're not going to do search for the entire blue area. Instead, you just look at the overlap. This is called overlap. Okay, so the search area is now limited to the pink, which is the overlap. Now, once you add the disconnected sites, so now not just connected site, but also disconnected sites. So disconnected site, they're going to actually help me reduce the area even further. So you can see this base station here, which is disconnected, it claims that coverage as the best server. So best server means dominant cell. So in these locations here where I'm pointing, this tower is the dominant. And if the victim is here, he would have connected to this tower, but he did not. Okay, so which means this area is an exclusion area. So we could exclude from the search area, which is the pink, originally this one. We could exclude from it this area here. So this will further reduce the area, the search area. So it's not just connected sites are relevant. Also, the non-connected sites can help you further optimize the search area by excluding the non-connected best server from the overlap. Now, the scenarios can be even more complicated. You might have a number of sites, not just one or two or three. So here you see we have 3 towers connected, 3 towers, and with this overlap pink area here as the search area. Now you see here we have 1, 2, 3, 4 disconnected. So these disconnected sites, the tool will use this information to reduce. You see, we excluded a part of the area and part of the area because these cells are dominant. So we could exclude them and further reduce the search area. So this is the convention of area optimization. So the examples I gave you before were based on circles, okay? So radius or search parameter. So in fact, you could deterministically predict and analyze reception. And we're going to use knowledge of the local area, such as the digital terrain model, the clutter, and the base station parameters, and so on. So we're going to use the antenna, the sectors, the azimuth, orientation, tilting, and all this technical information available to us in order to further optimize the model. So this is an excellent example. So on the left-hand side, you have a traditional way where you go and assume that the coverage is a radius, the coverage of a site. And that's not the reality of things, of course. So in that radius is going to give you, in the radius approach, is going to give you a massive area, of course. It gives you a circle. And that's what I showed you before. That's the traditional approach. Now on the right-hand side, you see there is a base station, a single base station, with the terrain behind it. Okay, so you can see the terrain. The terrain is not a flat. So you've got mountains, you've got hills, you've got canyons, you've got all sort of things. You've got also forest, vegetation, and so on. So you're looking on the right hand side. You're looking at the coverage of one tower, and you see how the coverage is not distributed equally everywhere. So the signal is not distributed in the same direction. and that's because of the terrain. For example, you can see in the area here, the terrain is acting as a natural barrier, and this is limiting reception in some areas. So if someone told me that a person I'm looking for was connected to this tower, there's no point you search in the area, for example, here. You see, there's no point to search here. So we're going to use the realistic environment, digital terrain, the clutter, the environment, the actual environment, in order to further optimize your predictions. So the coverage you're looking at here, this is the signal reception level. So neg 115 dBm up to neg 80 dBm. So here you're looking at reception for one site, up to 15 kilometers.